On January 28, 1986, the Space Shuttle Challenger disintegrated 73 seconds after its launch, tragically ending the lives of its 7 crew members on board. The tragic Challenger accident revealed deep systemic failures within NASA's organizational structure, where the normalization of certain technical anomalies was accepted as tolerable risks. But to analyze the sequence of events and the dynamics involved, we have developed a detailed technical analysis to determine why the Challenger accident occurred and what caused the shuttle's explosion. The STS-51L mission of the Space Shuttle Challenger orbiter was number 25 of NASA's spaceflight program, and its objective was to deploy a commercial communications satellite, conduct scientific experiments, and carry aboard Christa McAuliffe, a teacher selected for the Teacher in Space project as per mission profiles. This mission carried a strong symbolic weight within the United States space program, as it sought to reinforce the idea that access to space was beginning to become part of an increasingly frequent activity closer to civil society, progressively moving away from its exclusively military or scientific nature, which ultimately contributed to increasing media attention on this mission in broader public spheres overall. The crew consisted of 7 people: Commander Dick Scobee, pilot Michael Smith, and mission specialists Ronald McNair, Ellison Onizuka, and Judith Resnik. Also part of the mission were payload specialist Gregory Jarvis and teacher Christa McAuliffe, all of them with different technical and scientific backgrounds, reflecting the multidisciplinary nature of shuttle program missions. The Challenger had been designed as part of the Space Shuttle program, with a structure composed of a reusable orbiter that launched vertically, and 3 main engines fueled by liquid hydrogen and oxygen in standard use. In addition, 2 solid fuel boosters provided the extra thrust required in the initial moments of launch, these being responsible for most of the thrust during the first 2 minutes of flight, a phase in which the vehicle passed through the most demanding conditions from a structural and aerodynamic standpoint during liftoff. That morning, temperatures at the Kennedy Space Center were exceptionally low, far below any previous launch test. In fact, several engineers expressed concern about how the booster materials would respond under those conditions, especially the elastomeric seals that depended on their flexibility to function properly. Despite internal warnings and discussions between technicians and managers, the decision was ultimately made to proceed with the launch despite known concerns raised. The Space Shuttle Challenger lifted off at 11:38. The first seconds of ascent passed without visible incidents. The orbiter's 3 main engines and the 2 large solid rocket boosters worked together, propelling Challenger in a massive column of thrust and acceleration very efficiently upward. However, the unusually low temperatures that morning had affected the booster components, particularly the rubber seals known as O-rings, which were designed to hermetically seal the joints between the rocket segments and ensure proper performance. From the very first moments of launch, those seals, stiffened by the cold, failed to fully seal the joints, allowing high-temperature gases to begin leaking from inside the solid booster immediately. Barely 1 minute and 13 seconds after liftoff, records show that a leak of extremely hot gases began to emerge through the faulty joint in the right booster. At first, this leak was small and barely perceptible, but as the rocket gained speed and altitude, the gas flow progressively eroded the metal structure around the joint, continuously enlarging the damage throughout the early ascent phase. What began as a gas leak became a larger opening, and the jet of burning material started to burn through the structural supports connecting that booster to the external fuel tank, weakening one of the key attachment points of the system significantly. Meanwhile, the crew and mission control on the ground had no clear indication that something was wrong, as many parameters remained within apparently acceptable margins, and the control system compensated for minor deviations effectively. The pressure inside the tank began to drop abruptly, and at the same time the released gases caused one of the struts securing the booster rocket to the tank to break. That broken strut caused the rocket to shift violently, pivoting around its upper attachment point, pushing the tank and further damaging the structure. In just a few fractions of a second, the lower end of the right booster became misaligned, striking the external tank and puncturing it, which accelerated the release of hydrogen and oxygen. The combination of the rupture of the hydrogen tank, the mixing of cryogenic propellants, and the immediate ignition of these gases led to a massive explosion that disintegrated the entire shuttle stack. The progressive failure of the structure under extreme loads and the violent release of the tank fuels caused a sudden and devastating expansion of energy. Fragments of the orbiter, such as the wings, the main engines, and several other components, were ejected along different ballistic paths. The two boosters separated from the main assembly, continuing uncontrolled flight for several seconds before being destroyed by remote control. The forward section of Challenger, where the astronaut's cabin was located, separated from the rest of the vehicle and continued ascending, only to begin a falling trajectory seconds later. Investigations suggest that the crew cabin remained intact after the initial breakup, indicating it was not immediately destroyed by the vehicle's disintegration. 3 emergency air packs were found activated, implying that at least some crew members were conscious after the initial structural failure, although the loss of cabin pressure at high altitude likely caused a rapid loss of consciousness. The cabin impacted the water at an extremely high speed, estimated at over 200 miles per hour, which instantly caused the death of all crew members on board. After the accident, NASA worked together with the United States Navy and Coast Guard to carry out an extensive search and recovery operation. During the weeks following the accident, ships and various diving teams were used to locate the shuttle debris. Several key parts were recovered, such as the solid boosters, and the crew cabin confirmed recovery. In total, approximately 1/4 of the vehicle was recovered, allowing a precise analysis of the causes of the explosion. The official investigation, led by the so-called Rogers Commission, determined that the main technical cause of the Challenger accident was the failure of the O-rings in the right booster rocket due to cold temperatures. The investigation also pointed out management and communication errors within NASA and among its contractors, which led to the warnings from engineers about the risks of launching under those conditions being ignored, revealing structural problems in the organizational culture. The Challenger accident became a turning point in the history of spaceflight, prompting a profound reassessment of safety decision-making in high-risk missions, and how technical warnings were handled under schedule pressures and external expectations, ultimately shaping protocols that influenced all subsequent space programs. If you find our work interesting and would like to support us, you could subscribe and leave us a like. So in addition to helping us continue creating content, you can also stay up to date with all the news we upload to the channel. Finally, before signing off, we would like to know your opinion in the comments, and find out who you think is the true responsible party for the Challenger tragedy. Thank you very much for watching the video. We look forward to reading your comments, and we'll see you in the next video.